So last week we finished up talking about ionic bonds. And we said that they're different from covalent bonds simply because there's a transfer of electrons. So you've got a cation and an anion. And we said it's pretty easy to figure these out. All you need to do is figure out how many electrons were lost and how many electrons were gained, and that will determine the charge of your cation and anion. So we looked at sodium chloride. We said cations always have a positive charge, anions are negatively charged. And they do have a formula unit. So in the case of sodium chloride, it's always going to be in a 1-to-1 ratio. And then later on, we went and we talked about predicting charges. And we said there's a couple tricks you can do. The first thing is to look at the periodic table. If you're in group 1, 2, or 3, you can use the number to determine the charge of your cation. And if you're in group 5, 6, or 7, it would be -3, 2, and 1, respectively. So that's pretty straightforward. And then today we'll talk about those transition metals a bit more. And we said that in order to have a balanced ionic compound, you have to make sure that all your charges cancel. So there were a couple ways of doing that. One way was that way of doing Lewis-Dot structures that I showed you. And then the way I showed you at the end was take the charge of your cation and the charge of your anion and kind of flop them from superscripts to subscripts, right? And that can help you determine the charge. Okay, so now what we've got to do is we've got to figure out how to name these. We know how to get the molecular formulas, but we don't quite know all the naming conventions. So let's talk about how to name ionic compounds. And there's two types of naming systems. The first one is with group 1A or 2A cations. So that means that your metal is coming out of one of those first two columns on the periodic table, either 1A or 2A. Those ones are really easy to name. The next type is where you have a transition metal. Does anybody remember where the transition metals are on the periodic table? Yeah, the middle, right? So if you look at the periodic table, it's that big step down. It's that big block underneath there. So starting at group 3B, or I guess group 3 all the way over to 12, it's everything underneath that. Those are all considered transition metals. We have two different naming systems for those. Does anybody know why we have a different naming system for transition metals? What do you think? Exactly. The transition metals, I told you guys the charges vary, and so we need to be a lot more descriptive with their naming, as opposed to group 1A or 2A. Group 1 is always going to be +1, group 2 is always going to be +2. So let's do type 1 examples. So group 1A or 2A naming. Okay, so this one's pretty easy. All you do is you take your cation, this always goes first, and then space, and then your anion, whoop. And then you have an IDE suffix tacked onto the end. So let's take a look at a couple of examples. Got K2O. So what's the cation going to be here? Potassium or the oxygen? Potassium, right? Potassium's group 1A, so it's got to be our cation. So that goes first. And then oxygen goes next. But we don't have the full oxygen name. We change it to oxide, right? So this would be potassium oxide. One thing that throws people is that you don't use mono, di, tri, tetra. All of those prefixes aren't included because in this case it's assumed, right? So make sure you don't use those. You only use mono, di, tri, tetra, all of those with covalent bonds, not with ionic bonds. So let's do a couple others, and I'll ask you guys to help me with the name. So what do you guys think Ca3N2 should be?
I have some questions.
Yeah.
But is there like a simple way to like know when it's like ionic or like covalent to use the naming process?
That's a great question. So you were asking how can we quickly tell if it's ionic versus covalent, right? So the easiest way to tell if you've got an ionic bond is that you have a metal and a non-metal. So something on the far left-hand side bonded to something on the far right-hand side is going to be ionic. That's the easiest way of telling. If you've got two things in the top right-hand corner, they're usually covalent. So in this case, potassium's on the far left-hand side, oxygen's on the right. That's a big clue it's ionic. Good question. So Ca3N2, what would we name that?
Calcium nitrate.
Calcium nitrate or what would the suffix be?
It would be
Ide. So calcium nitride. That's one thing people get confused on is they're like, well, when do I use the ATE suffix? That means something very different, and we're going to cover that shortly. So make sure you have the IDE suffix for these. All right, what about the next one? Calcium sulfide. Okay, so these are pretty straightforward and easy, right? Yep.
So back in your table of periodic table, there were a couple transition metals that had the charges written. Are those going to be using this method as well?
No. So with transition metals, we will not use this naming convention. We have to use a different one. So I'll show you guys that next. That's a good segue. So let's do transition metal naming. And we said that those transition metals are in that center block of the periodic table. This one has a pretty simple naming convention, but it does vary a little bit. So just like before, we put the cation first, and then you have a Roman numeral after. And then space, anion, and then you have this IDE suffix tacked on. So this Roman numeral is very important. We said that the charge of a transition metal can vary. All this Roman numeral does is tell you what the charge is of your cation. Also, just like before, we're not going to use mono, di, tri, tetra, or any of those because it's ionic. You only use those with covalent compounds. So let's try a couple of them. Let's try FeCl3. So in this case, iron, if you look at the periodic table, is number 26. It's in that center block. So that indicates we need to use a Roman numeral. And it is a metal and a non-metal, which confirms that it is ionic too. Okay, so let's do our cation first. It's going to be iron. Then what charge do you think the iron must have? Let's think about this, right? So let's break it up. So we've got this iron here. We've got one of them. We don't know the charge yet. That's what we're trying to figure out. And then over here we've got 3 chlorines. What charge does chlorine have? Yeah, -1. It's in group 7, which means all of these must have a -1 charge. Okay, which means in order for this to be balanced, iron must have what charge? +3, right? Okay, so we can break this apart and we can say, all right, iron must be +3. So if we go over, we'd say iron, and then in brackets, Roman numeral 3. And then what would go next? Chloride. The number one mistake I see people make is they'll say iron 3 trichloride. You don't have to say trichloride. The fact that it's iron 3 means you must have 3 chlorines, right? It's an assumed thing. So the 3 just simply represents the fact that the iron must have a positive 3 charge. Let's try a couple other ones. Let's do CuBr. So same sort of thing here. We can break this up and we can say, all right, we've got copper, we don't know what charge it has, and we've got bromine, which must have what charge? -1. It's in group 7. Okay, so knowing the fact that we have one bromine with a -1 charge, the copper must have what charge? +1. Okay? Okay, so now let's go ahead and name it. It would be copper 1 bromide. The 1 indicates that we do have copper 1. This would be different than CuBr2. What would we name CuBr2? Copper 2 bromide, right? Because in this example, if we break it up again, we'd have copper with some unknown charge, and then 2 bromines, each that are -1. So in order to cancel out the -1 off of each of the bromines, this copper must be 2+, which means that this would be copper 2 bromide. Does that make sense? I know it can be a little bit confusing, but I'll get you guys a nice flow chart and then we'll go through a good practice activity when we're done here. All right. Just because this wasn't challenging enough, I have to throw a curveball at you. These are polyatomic ions. Polyatomic ions are kind of confusing, so we'll go through them a little bit slowly. They are a charged species containing more than one atom that is covalently bonded to another. And these are a little bit confusing, but I'll show you guys a pretty basic example. So let's take sodium hydroxide. This is used for making soap. It's very basic. And we can piece this apart, right? So let's take a look at the sodium first. What charge does sodium have? +1, right? Okay, so sodium we know is group 1, so it must be +1. And then we look at the rest and we'd say, well, it's not just oxygen. There's an oxygen and a hydrogen. So what we're going to do is treat this as one full unit over here. And I'd say OH. And what charge do you think this OH would have in order to make things balanced? -1, right? So we'd say, all right, this entire OH group has a -1 charge. It does get a little bit confusing, so let me show it another way. I'll show it down here. So let's say we've got sodium. We know sodium is a metal with one anion, or one electron, excuse me. And then hydroxide we know is OH. Oxygen has 6 valence electrons. Hydrogen over here has 1. Right, so this would be the Lewis dot structure for all of these elements. Hydroxide itself is a unit that contains a covalent bond. So what ends up happening is these 2 electrons will pair up to form a covalent bond, which makes sense. So I'm just going to show this as a straight line. Okay. And then if we look at oxygen, oxygen doesn't have paired electrons on that bottom side. So what it's going to do is it's going to take this electron from sodium, which will result in the sodium missing its electron, giving it a +1 charge. And then this oxygen over here now has all paired electrons, giving this oxygen a -1 charge. So can you see that even though OH contains a covalent bond, it's treated as an anion because it's got an extra electron. This is still considered ionic, even though there's a covalent bond present. So let's make a little note. Whoop. Why can't I spell anion today? It's an anion that contains a covalent bond. Okay, there are a handful of these that I am going to ask that you guys memorize. And this is simply because they're very common in the medical community. So in your book, if you go to table 4.4, you'll see a big long list. I do want you guys to memorize the ammonium ion, which is NH4+. I want you guys to memorize hydrogen carbonate. I want you to memorize acetate, nitrate, cyanide, hydroxide. We'll skip a few. We'll go to carbonate, sulfate, and then last but not least, phosphate. I know these are a lot to remember, and so what I've done for you guys is I've made something called a Quizlet game. Has anybody used Quizlet before? So Quizlet is pretty nice. Let me pull this up. Quizlet is basically an online flashcard game, and I'll show you guys briefly how it works. Let me close this one out. Oh. So if you open up the link, it says Chem 110 polyatomic ions. You've got a couple different things you can do. One of them is flashcards. So if you click on flashcards,
PO43-.
say, all right, PO43-. What's the name of this? And then you can check yourself.
Phosphate
hit it,
ion.
And you say phosphate ion. And then the next
ClO3-.
one, ClO3, and you'd be like, oh shoot, I forgot the name of this one. And then tap
Chloride
on it.
ion.
Oh, it's the chlorate anion. And so you can use that as a really simple, quick game. Let's go back to the other ones. The other one is the learn one, where you can just check your spelling and make sure you're spelling everything correctly. There's another cool one too that's a gravity game, where you can actually compete with other classmates, I believe, and see who has the high score. And then when it falls down, you can quickly type in the name and test yourself. It's pretty funny. Students in my organic class get really competitive with Quizlet, and they try to beat each other's high scores. So you guys are welcome to do that too. All right, so let's go back. And let's do a few examples here. And I'll try to make it pretty straightforward for these. So let's do NH4Cl. So NH4Cl, students are oftentimes tempted to look at this and they'll say, there's not a metal in there. That means that it should be named using the covalent mechanism, right, or the covalent naming technique. But then we would say, wait a minute, NH4 is one of our polyatomic ions. That means that it's an exception to the rule. So if we look at it, NH4 has its own special name. What is that called? Yeah, it's ammonium ion. What charge does an ammonium ion have, if you're checking your book?
1.
+1. Okay, and then over here we've got this chloride anion. And what charge must the chloride anion have? -1. Okay? So if we go through and we name this, what do you think we should name this? So we only use Roman numerals with transition metals only. So in this case, we don't have a transition metal, although that's a good guess. So what do you think we should name this? So we go cation space anion with the IDE suffix. So this would just be Ammonium chloride. And let's try to make sense of this using some Lewis structures, right? So let's first determine the Lewis structure of the ammonium ion. So we know we've got NH4. How many valence electrons does nitrogen have? 5. Okay, so I'll go ahead and I'll say 1, 2, 3, 4, 5. Hydrogen must have 1. Okay, so we can try to form covalent bonds here. So I'll form a covalent bond between those two. Covalent bond between those two. Covalent bond between those two. And then we're running into a problem over here, right? We can pair up one of these, but we have an extra electron. We can't have more than 8 electrons around an atom, right? So we're running into a problem. We've got to take that electron and give it up. So what I'm going to do is I'm going to just circle this and I'm going to say remove 1 electron. Okay, so now if we go ahead and we look at this, we'd have hydrogen bonded to a nitrogen, bonded to a hydrogen, hydrogen, hydrogen. We kicked off that 1 electron, but this entire group, because it lost an electron, must have a positive charge, right? So +1. Does that make sense? So you can use that as a quick way of telling what charge these simple polyatomic ions have, is try to draw the Lewis structure. If you've got extra electrons, pluck 1 out and then fix the charge. If you don't have enough, you may need to add more electrons back in. So let's try another one. Okay, so let's try following these rules. First one is draw the Lewis dot structure. Number 2 is add or subtract electrons so that all electrons are paired and all atoms have an octet. Of electrons. So let's do this one first. We'll do NO3, and without checking in your book, let's try to draw the Lewis structure and then add and subtract electrons as needed so that all electrons have a partner electron and each atom has an octet. And this is our nitrate anion. So nitrogen in this case will be the center. I'll give you guys that hint. And we've got 3 oxygens out here. How many valence electrons for nitrogen? 5. Okay. 1, 2, 3, 4, 5. Okay. Oxygen? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, not too bad. Now we need to pair up electrons, right? So we've got to have a covalent bond, at least one, between each of these. All right, so let's focus on this oxygen over at the left, right? It's got 1 extra electron. What might we need to do? Can we form a covalent bond there? Right now it doesn't have an octet and it's not paired. What do you guys think? Anybody have an idea? So remember back up here I said we can add or subtract electrons as needed. Right now this oxygen is missing an electron, so what I'll do is I'll say, all right, let's just add an electron right here so that that oxygen now has an octet. Does that make sense? Okay, so that makes sense. What about the next oxygen? Same thing? So we can do that. Okay, there is another problem though that I'm seeing. Let's say we try to do it with this one and we say, all right, let's hook an electron into that oxygen. All the oxygens would be happy, but what do you notice about the nitrogen right now? It's got 2, 4, 6, 8 electrons. Yeah, we could try doing that, but let's try something else. That'd be a really charged species to have 3 negative. What if we partner up this electron, and then we're going to take this electron out. So we'll form a covalent bond. Now let's try redrawing this. And now we've got oxygen, single bonded to nitrogen, single bonded to oxygen, double bonded to oxygen. This oxygen on the right has 2 lone pairs. Okay, this oxygen we added an electron into, right? So what charge should that oxygen on the left have? So if we gave it an electron, just -1, right? It's got a -1 charge because it's got that extra electron. Same thing with this one up here. It's got an extra electron. This one over here, we didn't add or subtract electrons to, so that one's just going to be neutral. So I'll go ahead and write 0 here. And then what about this nitrogen? It's got 8 electrons around it, but we removed an electron. +1. And then if we look at this whole unit, what's its overall charge going to be? -1, right? So 2 minus would cancel out with one of the +1s, giving it a -1 overall charge. Does that make sense? So that its net charge is -1. These do get pretty complicated. Honestly, we're going to be testing you guys on the basics, so I do want you guys to memorize the name and then their overall charge. But if you go on in general chemistry, you're going to have to draw the more complicated structures.
How come you couldn't take one of the oxygens and add it to the nitrogen? Like how you did, like you know how nitrogen's like.
Oh, so you're saying why not take one of these and huck it over there?
Yeah.
You can think of it that way too, right? So I'm just trying to show that we were adding or removing electrons, not necessarily where they were going to.
Would you still get the same answer if you did?
Yeah, you would still get the same answer if you did it that way. That's a good question.
Where are those electrons coming from? They're just falling.
So just with ionic bonds, they're really stable. Having that charge, the question is where do they get that? It depends how it's made. Yeah. All right, so let's do some practice, and then I'll hand out a worksheet for you guys to work on. So the flow chart. Is your compound, I'm going to abbreviate compound, ionic or covalent? Okay, not too bad. And then we're going to break this up. We'll say covalent. And what's the way we can tell if a compound's covalent? Yeah, by electronegativity. The other thing we said is covalent bonds are usually between nonmetals, right? So only nonmetals. However, the thing you've got to watch out for are those polyatomic ions. We said that polyatomic ions occasionally have only nonmetals, but they're still considered ionic. So covalent bonds are things that are only nonmetals and do not contain one of the polyatomic ions. Not too bad. And then over here we've got our ionic group. And we said these are usually between a metal and a nonmetal. Or contains a polyatomic ion. Sorry about my handwriting here. Let me scoot this over. Okay, so that's the first thing I do is before I get started with naming at all, I try to classify it as covalent or ionic. Covalent ones are pretty easy, right? What was the rule with naming a covalent compound? Close. So naming for covalent compounds, we don't have a cation, right? So it's your first atom. And you may need a prefix. Second atom with an IDE suffix. So let's do a couple of examples. Whoop. Or we'll just do one example and then we'll jump into practice. So H2O. If we're naming this, we've got hydrogen as our first atom. Do we need a prefix? Yeah, there's two of them, right? So we don't include mono if it comes first. However, in this case, we don't have only one. This would be dihydrogen monoxide. So it's important that you have both the prefixes and then that IDE suffix. Does that make sense? Okay. And then we're going to take a look at this ionic one again. And we said that ionic kind of falls into two categories. One is where it's a group 1A or 2A cation. And then what was the other one? Yeah, just transition metal cation. Okay, and then for naming, it's pretty easy. For this one, we just have our cation first, and then anion with an IDE suffix. So an example that we had that's really easy to remember is NaCl. Sodium's in that group 1. So this would be sodium chloride. Not too bad. All right. And then let's refresh our transition metal one. We've got our cation, our number that's a Roman numeral. Let me slide this over. And then anion with an IDE suffix. So our example here could be something like, let's just stick with one we've already covered, CuBr, where it be copper 1 bromide. And we have to remember the Roman numeral for those. Does that make sense? I know this is confusing at first, but the more you practice it, the easier it becomes. So let's do a few practice ones, and then we'll see if we have time to work on the worksheet today. All right, so the first thing I want you guys to do is determine if it's ionic or covalent. 2 is draw the Lewis structure. Determine the molecular geometry or shape. And this is for covalent only. We'll not do that for ionic. And then 4, we'll do the name. Okay, so the first one, we'll do MgCl2. You guys think this is ionic or covalent, and why? Ionic. Why is it ionic? Because it's on the far left-hand side for the magnesium? Yeah, I'd agree. That's a definite ionic compound. We've got a group 2A metal, and we've got a non-metal. So this has got to be ionic. Okay, and then the Lewis structure. What charge does the magnesium have? +2, okay. So this would be 2 plus, and then chlorine over here normally has a valence number of 7, right? But in this case, it's got an extra electron. So this would be -1, and we've got 2 of these. So we'd have 2 negatives, right? This is good, though, because our charges are balancing out. We'll skip number 3. And then number 4, what is its name? Magnesium chloride, exactly. So it's a ionic naming system that doesn't use the transition metals, so we don't have to include the Roman numeral. All right, let's try another one. I'll do a morbid one. Let's do HCN. This one's a little tricky. Actually, I'm going to change this. I apologize. Let's do KCN. Make it a little bit easier. So is this ionic or covalent? It's ionic, right? We've got a metal in there, so it's got to be ionic.
If it was the H, or if it was HCN, would it be covalent?
It would be, yeah. That's a kind of odd example, though. So let's do this. We've got ionic. Let's do the Lewis structure, though. So potassium always has what charge? +1. Then we've got CN. What the heck is going on with CN? It's carbon and nitrogen. That's one of our polyatomic ions. What's that polyatomic ion called?
Nitrate.
CN?
Oh, C.
Yep.
Cyanide.
Cyanide. Okay, so it's cyanide. What charge does cyanide have? -1. Okay, so we know it's Cn -1. If we want, we can go through and draw the Lewis structure of that real quick. We know that carbon has 4 valence electrons. Nitrogen always has 5. Okay, so what we're going to do is we're going to try to pair these up. And then if we look over here, this side's missing an electron, so we're going to add an electron. Okay, which means when all is said and done, this is a carbon-nitrogen triple bond, where the nitrogen has a lone pair and the carbon has a lone pair, giving the carbon a -1 charge on it. So we can even go through and say, all right, this is carbon-nitrogen, and we've got -1 on the carbon. So this is an ionic compound, even though it contains that polyatomic anion, cyanide.
Why is the potassium involved in the Lewis structure?
So potassium always has a +1 charge. So if you think about potassium like that, it's really unstable having 1 electron. So all we're going to do is remove it. So its Lewis structure looks like just a K with no dots around it, but an overall +1 charge. That's a good question. Okay, so now we're on 3, but again, 3 is not applicable. And then what will its name be? Yeah, just potassium cyanide, exactly. This stuff is super toxic. If you've ever watched the old spy movies where people take the pills and they like bite on them and they kill themselves, that was actually potassium cyanide. It's a really awful poison. So this is potassium cyanide. It's actually really similar to carbon monoxide. Do you remember the other week when I was saying carbon monoxide will bind to your blood and not let go, meaning your oxygen can't bind? Cyanide does the same thing. It will bind to your blood and not let go, and you actually suffocate. It's a pretty awful way to die. All right, let's do another one. Oh no, I'm running out of room. Let's just do some practice down here. We'll do some more naming after this. All right, so the correct formula for the ionic compound formed from the elements potassium and oxygen would be which? See if you can figure it out and then check with your neighbor. We've got potassium right here. We've got oxygen right here. Give me a thumbs up if you agree with your partner or your neighbor. A few thumbs. So potassium always has +1, right? Oxygen always has what charge? Okay, 2 negative. If you remember that trick I showed you, this is going to be moved to that suffix, and this is going to be moved to that suffix, which means the overall molecular formula should be what? Yeah, K2O. Okay, which means that B has got to be the right answer here. I think there are some sapling problems that are similar to this. I know it is super duper tempting to look at that Google search bar and say, I should just type this into Google. That won't help you on the exam, so try to figure it out. And then if you're truly stuck, don't be afraid to email me. I understand this stuff is really complicated when you're first learning it, so feel free to email me. Let's do another one. All right, what is the correct name for this compound? CuCl. So if we use the flowchart system, is it ionic or covalent? Ionic, copper's a metal. And then we have to determine Does it have a transition metal or no transition metal? Transition metal. So we do need to use the Roman numerals because there's a transition metal. All right, so if we look at this, we'd say, all right, we don't know the charge of copper, but we do know the charge of chlorine. What charge must chlorine have? -1, right? Which means that our copper must have what charge? Yeah, it must be +1 in order for the charges to cancel out, right? So now looking at the name, which one makes the most sense? B. Students are really tempted to say copper monochloride, but people will look at you funny if you say that. If you remember, don't use those prefixes unless it's a covalent compound. Let's do another one. All right, which of the following would be the correct electron dot structure for nitrogen gas, N2? So let's even just build it on our own without looking. Nitrogen has how many valence electrons normally? 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we need to pair these up. This is a covalent compound, so we're not going to add or subtract electrons. So we're just going to try to pair it up the best we can. Okay. That means each nitrogen still has a lone pair left over, right? So if we look at this one, the best match would be which one? E, absolutely. All right. Next one. Carbon monoxide is a colorless, odorless, toxic gas. Which of the following best describes this molecule? First of all, do you think it's an ionic bond? No. Okay, so process of elimination, we can rule that out. We don't have a metal in there. We don't have a polyatomic ion in there, so it can't be ionic. Okay, B. Does it have polar covalent bonding with the carbon being more electronegative, or does it have polar covalent bonding where the oxygen's more electronegative, or do you think it's nonpolar? First of all, let's determine whether or not it's polar or nonpolar. What do you guys think? It's got to be polar, right? Nonpolar means it's equal sharing. We know oxygen's further to that right-hand corner than a carbon. So let's rule out D. And then let's draw the structure to determine which one's more likely. Okay, so carbon normally has 4. Oxygen normally has 6. Okay. So if we go ahead, actually, we can solve this even without the Lewis structure. What do you guys think? Yes, C, because oxygen's more electronegative. We don't even need to draw the Lewis structure for this, so let's just go ahead and jump straight to C. All right, and then I think we've got 2 more, and we'll call it. All right, according to valence shell electron pair repulsion theory, a molecule with 3 bonding pairs and 1 lone pair will have what shape? So basically saying it's got a central atom, 3 things like this. I'll call this X, 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 and then a lone pair hanging out up here. Which shape is this? C, trigonal pyramidal. And then last but not least, we'll hurry. Which of the following best describes the bonding and polarity of dichloromethane? Does this have polar bonds? Yeah, chlorine's in that top right-hand corner, right? So we could say definitely chlorine's going to hog electron density away from this carbon. Does it have a net dipole? What do you guys think? Or is everything bounced? Is everything pulling in equal and opposite directions? I would say they're pulling overall net towards that side, right? Because those 2 chlorines are in the same direction. So this would have a net dipole. So if we look at all the answers, we have both polar bonds and the molecule itself has a net dipole, which means that D is the right answer. All right, so tomorrow we're going to dedicate the entire day just towards naming practice. So I really encourage you guys to come and we'll just work through a big, long naming worksheet. It's a good way of reviewing.